Hi viewers, welcome to LMS Solution. Today we are going to see about MATLAB simulation of physiologic based variable step size P&O MPPT algorithm for solar PV system. So thanks for watching our videos. Kindly subscribe our channel and also click bell icon for a notification about upcoming videos. So first you have to see about the flowchart for the physiologic based variable step size P&O MPPT algorithm. So this is a flowchart for logic based variable step size P&O MPPT algorithm flowchart. So here we need to measure two parameters. So one is PV voltage and current, and then you have to calculate PV power, and then you have to calculate change in power and change in voltage. Okay, that means so you have to compare the power level with the current instant with the previous instant, and then for finding the change in voltage, you have to compare that current instant voltage with the previous instant voltage. So next you have to uh, divide that del PV with del V. So this is one of the input for that physiologic controller. So another input nothing but fixed protection step size. So this is another input for that physiologic controller. So the output of this physiologic controller is a small change in voltage. So that going to be added with the PV voltage, or else the output from the physiologic controller is we can consider as small change in duty cycle. So that going to be added with the previous duty cycle. Okay. So just you have to update the duty cycle or PV panel voltage. So based upon two input. So del PV divided by del V. Okay. So here the input will be del P divided by del V. So we can call this a slope. Okay. Slope of the PV characteristics of the PV panel. So another input nothing but a fixed protection step size. Okay. So based upon this input, you have to decide the variable step size for that P&O algorithm, normal P&O algorithm, right? So now in normal P&O algorithm, what we are going to do? So first we have to check the change in power, whether it is equal to 0 or not. Whether if it is equal to 0, then no need to change anything. So no need to change, that mean no need to change the PV panel voltage, no need to change the duty cycle. Okay. So that mean already the PV panel is operated at the maximum power point condition. Okay. If suppose the del PV is not equal to 0, then we need to compare, that means we need to check the condition of the del PV. Okay. So that means whether the del PV is greater than 0 or not. That means we have to check the sign of the del PV. Okay, whether it is positive or not. Okay. So if it is positive, right? So if del PV is greater than 0, then what's the meaning? The sign of the change in power is positive, and then sign of if suppose del PV is not greater than 0, the sign will be negative, right? So if both condition, if sign of the change in power is positive or negative, so next obviously we go to check the another condition, I think, but you have to check the condition whether del VPV or del V is greater than 0 or not. That means del VPV is positive or not. Okay. So if del PV is positive, right? So then we need to update the PV panel voltage by adding the small change in voltage. The PV, right? PV voltage is we are going to change the PV voltage by adding small change in voltage, right? So the small change in voltage comes from this physiologic controller. So based upon these two input, del PV divided by del V and fixed as step size. Okay. So when it is negative, right? When it is negative, then we need to decrease the PV voltage by the amount of del V. So this del V also comes from physiologic controller. So when this is for del PV is greater than 0, that means the sign is positive. Next we got to check the del V. If del V is positive, then we got to increment the voltage by the amount del V. The del V comes from physiologic controller. When del V is negative, then we need to decrement the PV voltage by the amount of del PV. So this is comes from that physiologic controller. The same way you got to next you have to check the condition whether that means del PV is not greater than 0. That means the sign will be negative. Okay. Once again you have to check the del PV. So whether del PV is greater than 0 or not. So whether it is positive, del V is positive or not. Del PV is positive or negative. If it is positive, then we need to increment the voltage, PV voltage by the amount of del V. If it is negative, we need to decrement the voltage by the amount of del V. So the del V comes from the physiologic control. So here the del V is going to be variable, right? So the del V going to be decided based upon that the slope of the PV panel, PV characteristics. Okay. So then that value from the physiologic control, that means that small change in voltage or small change in duty cycle, right? So here we are explain the algorithm based upon the voltage, right? So when you when you got to apply the same algorithm for that PV panel is connected to the load connected load via converter, right? That so we need to adjust the duty cycle, right? So that means the physiological controller should provide a small variable change in duty cycle. Okay, variable step size duty cycle for that P&O algorithm not to change the duty cycle and to get the maximum power from the PV panel. So this is the flow chart for that physiologic based variable step size P&O MPPT algorithm. So first we need to design this. So fuzzy logic based, that means this fuzzy logic controller based upon these two inputs. So we need to fix the membership function for this first input and second input, and then you have to fix the membership function for the output, that means small change in duty cycle. Okay, so let me see about that concept in the MATLAB. So first I'm going to open the fuzzy tool, designer tool, right? And then I'm going to open the fuzzy logic designed model. So this is the fuzzy designed model. So first input nothing but fixed step size, and second input I'm going to here consider is slope, right? So this is a value for that fixed step size, and then that mean membership function for that fixed step size, and then this is membership functions for that slope, otherwise we called as del p divided by del b, and then this is variable step size, that means change in duty cycle. Okay, this output of that physiologic controller. So next we created nearly 25 rules. So you can see here, I'm going to open that rule. So when the fixed step is around 0.075 and the slope is 0.025, the variable step size is equal to 0.015. So I'm going to change the slope. So you can see the variable step size or variable small change in duty cycle. Okay. So when that del p and del v changes, right? So automatically it adjusts the output duty cycle, right? So and also I'm going to adjust this fixed reduction step size, right? So when I'm going to change this one, So output also going to be changed. So okay, so this is the variation of that two input, right? Fixed step size and then slope. So based upon these two input, the output variable steps is going to be changed. Output variable steps is duty cycle going to be changed. So this is going to be added with that. This is going to be used to for update the duty cycle of the P&O algorithm in the P&O algorithm. Okay. So next I'm going to show you that model. So this is a model used for implementing that fuzzy logic based variable steps P&O MPPT algorithm. So it consists of a solar PV panel. So here we are consider a 250 watts PV panel, and then here we are consider that mean two inputs, right? One is irradiation, another one is temperature. So here I'm going to fix the temperature is around 25 degrees Celsius, and then I'm going to take two conditions. One is constant irradiation, and then dynamic irradiation condition, or static irradiation condition, and a dynamic irradiation condition. So you can switch over this condition by using this manual switch. Okay. So here I'm going to fix the irradiation level from 1800, 600, 400. So they're going to be changed every 0.2 seconds. Okay. So the irradiation of the solar PV panel going to be changed every 0.2 seconds. Okay. So and next you can see that here we are using that boost converter. The boost converter is connected to the load, right? So here we are using three loads, R1, R2, R3. So why we are using this three load, right? So we are going to test the model with the changing load condition also, varying load condition also, right? So for the purpose only we are using this one. Okay. And then here you can see that we are uh, using that fuzzy based variable steps P&O MPPT, right? It's going to be receive two inputs, PV panel voltage and PV panel current, and then go inside that. So this is the Simulink model for a physiological based variable steps P&O MPPT algorithm. So here you are going to show V of n, I of n, and then you have to calculate and del, that means E of n minus E of n minus nothing but V of k minus V of k minus 1. Here we are measuring I of k minus I of k minus 1. And then finally you have to calculate del P, right? Okay. So this del P, so when we divide with the del V, right? So this is nothing but del P divided by del V, and then this is fixed step size or fixed protection step size, right? So is given to this here, right? So the output will be small change in duty cycle, otherwise called delta T. Okay, so this is going to be given to the P&O algorithm. The same P&O algorithm is going to be received two input, PV voltage and current. Okay. So next, go inside this algorithm, right? We have to receive three inputs, PV voltage and PV current, and a small change in duty cycle. The small change in duty cycle comes from the fuzzy logic controller, right? So this is going to be added with the previous duty cycle. So based upon the condition del V and del P. Okay, so this is a normal P&O algorithm, but here we are going to use variable step size duty cycle. Okay. So finally we will get that duty cycle here. So this duty cycle then is going to be processed via the PWM generator. So the PWM generator, that means it's a duty cycle. So it's going to be compared with the sawtooth waveform, right? Then we will get the PWM pulse side, pulse width modulation, PWM pulse. So that pulse going to be given to that IGBT in order to control the boost converter for extracting the maximum power from the PV panel. Okay, so this is the operation of this simulation model. So first I'm going to consider varying, that means dynamic change in irradiation condition, right? And then I'm going to fix the load constant. So I'm going to fix the load constant, and then I'm going to check the output of the system. Okay. So here we are measuring the different parameters. That means here you can see here, right? This is nothing but PV voltage, and then this is output of the converter. So this is PV current, and then boost converter current, output of the boost converter current. This is PV power, and then this is boost converter output power. Okay. So this is PV power. So next I'm going to simulate this model. We can see the variation of the voltage and current and power with respect to change in irradiation. So here you can see that, so the irradiation change from 1000 watts per meter square to 800. So the PV power is extracted exactly. So let me tell you how is extracted exactly. So we'll just compare with theoretical value, right? So this is for 1000, this is 800, this is 100, and this is for 400 watts per meter square, right? So this is a change in PV voltage, and then this is change in boost converter output voltage. So this is a change in PV current. So this is change in boost converter current. So this is change in boost converter power. Okay. So next I'm going to tell you how we are going to compare the result, right? So here just you have to click this PV panel, right? And then in this side you can see that you can plot the IV and PV characteristics of that solar PV system or solar PV panel, right? So here I'm going to consider one model at 25 degrees Celsius with the specified irradiation level. So I'm going to vary the irradiation from 1800, 600, 400 for different setting of that irradiation. I'm going to plot the IV and PV characteristics. Okay, I'm going to click this one. So here you can see that IV PV characteristics of that the consider solar PV panel. So it going to be compared with that PV power extraction, right? So here you can see here for 1000 watts per meter square. So this is a maximum power point is around 250, right? So here you can see that for 1000 watts per meter square that power is. So let me open another thing, right? This is also open this one, right? Yeah. So here initially from 0 to 0.2 the irradiation is 1000 watts per meter square. So here the maximum power theoretical power is 250.2. So here we are getting around 250 watts, right? So next from 0.2 to 0.4 irradiation is 800 watts per meter square. So here you can check the power is around 200 watts, right? So here also you can see that the power is 200. So when from 0.4 to 0.6 the irradiation is 600 watts per meter square, and then the power, the peak power is around 150 watts. So here also you can see that we are getting around 150 watts. From after 0.6 the irradiation is 400 watts per meter square. Okay, so from 400 watts per meter square the power, the peak power is around 98.97. So here you can see that the power is extracted from, that means is around 98.97, right? So the maximum power is extracted from the PV panel for change in irradiation condition. Okay, so and also you can see the current level, for example here, right? For different irradiation condition. For 1000 watts per meter square, the current level is around 8.15. So here you can see that the current level is around 8 amps. So for 800 is around 6.5. So here also you can see that it's around 6.5 something. For 600 is around 4 point something. So 4.8. Okay, so here you can see that 4.8. So I'm going to explain with the measurement, right? So I'm going to adjust this one. So here you can see that is around 7.96 amps, right? For 1000. So for 800 the current around 6.43. For 600 it's around 4.9 or 4 point, yeah, 4.82, but here 4.89. Okay, so for 400, right, is around 3.3. So here you can see that 3.1. So we kept in the random point, right? So but you can check this exact peak point, right? Then you will get exact current level. So but that extraction, during extraction of peak power from that PV panel, the current will be matches nearer to that peak point, right? Peak point, current at peak maximum power point, right? So next I'm going to show you that the voltage. So this is a voltage across the PV panel. So here you can check that one. For 1000 watts per meter square, the voltage is around 30.7. So here you can see that the voltage is around 31 point. Okay, so it's near to that peak point level. So for 800 is around 30.8. So here you can see that. So this is also around 31.28, and then for 600 is around 30.6. So here also you can see 30.45, 30.6, and for 400 watts per meter square, the voltage is around 30.41. So here you can see that. So it's around 29.86, right? So the voltage, operating voltage of that PV panel, operating voltage of the current is nearer to that voltage and current at maximum power point level in theoretical. Okay, so that's why that power is extracted from that PV panel, so by means of the fuzzy logic based variable step size P&O MPPT. So this is the working of this model. So thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming video. Thank you. Thank you once again.